Triple integrals in spherical coordinates. For some functions and domains, a new coordinate system called the spherical coordinate system is often advantageous. Let's first talk about how we graph points in the spherical coordinate system. So imagine we have our standard x, y, and z coordinate system. If we have some point P, which corresponds to some value on the x-axis, some value on the y-axis, and finally some value on the z-axis, we can give that point new coordinates by defining it in such a way. So if you look over here at this other graph, instead of using x, y, and z to locate the coordinates of this point, first we will consider the positive x-axis and the angle through which we have to rotate to get to point P. And then we'll look at the angle that we have to rotate from the positive z-axis to get down to P. And finally, how far is the point from the origin? So those coordinates are actually listed as rho, the distance from the origin, first, the angle from the positive x-axis, second, and the angle from the positive z-axis, third. And those coordinates are rho, theta, and phi. And I'll go ahead and spell those out. And, of course, we know what theta is. Rho is spelled R-H-O, and phi is P-H-I, and some people pronounce phi as phi. I always call it phi, though, and that's what I'll be using in this video. So next we need to talk about the relationship between the coordinates x, y, and z and the coordinates rho, theta, and phi. And so we have those relationships expressed down here, but I want there to be an understanding of where these come from. So let's go ahead and see if we can derive these formulas. The first formula here is pretty easy to derive. So we know that this here is a right triangle, and one of the legs is r, and the other leg, of course, is this distance here, which is z. And that means that r squared plus z squared is equal to rho squared. But then down here, we also have a right triangle. And in that triangle, we know that x squared plus y squared is equal to r squared. And so if we simply substitute x squared plus y squared into r squared here, we end up getting x squared plus y squared plus z squared is equal to rho squared. So this first formula here is pretty easy to verify. Now for the other formulas that you see down below here, we need to identify some of the angles that we have in these triangles. So first of all, we have the familiar triangle down here. I say familiar because this is the same triangle that you talk about in the polar coordinate system, where you have x and y and r, and then of course this is theta. And in that system, we know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now, if you look at the other triangle right here, we know that the angle phi is from the positive z-axis down to this line. Now, because this line here is parallel to this line, we know this angle and this angle must be the same. Those are alternate interior angles, so they must be congruent. And now up here, we can define z in terms of r and phi. So z is this side right here, and we know that z is equal to, actually I said r, I meant rho, sorry. We know z is equal to rho times the cosine of phi, so we'll go ahead and write that down. But the spherical coordinate system doesn't have an r in it, right? It's only rho, theta, and phi, so we want to get rid of the r that we have here. And we can do that by using this other triangle. R and phi and rho have a relationship, and that relationship is sine of phi equals R divided by rho, or R is equal to rho times the sine of phi. And now all we need to do is take this expression and replace the R here and here. And you can see what happens when this is done. But if I take that should say rho sine of phi, not rho sine of theta. Okay, there we go, fixed it. If we take that and plug that expression in here, then we get x is equal to rho sine of phi cosine of theta. If we put that expression in here, we get y is equal to rho sine of phi sine of theta. And of course, z is already rho cosine of phi. And these are the equations that will translate x, y, and z into rho theta and phi, or vice versa, rho theta and phi into x, y, and z. So let's do a couple of basic examples here. We have the point 2 pi over 4 and pi over 3, and that's in spherical coordinates. We want to plot the point and also find its rectangular coordinates. So to plot this, we are going to rotate through an angle theta, which is pi over 4, and that is approximately this angle right here. And then rotate through an angle pi over 3 from the positive z-axis. So that's going to come down in this direction. So basically coming down in the same plane as this angle. And then we are going to go a distance of 2 units from the origin. And so it's very difficult to show exactly what that would look like. But this angle down here is pi over 4. This angle up here is pi over 3. And this distance right here is 2 units. And now to find the rectangular coordinates, all you would have to do is plug in these values you see here into the conversion formulas. And here it is when you plug all those in. And so we have radical 6 over 2, radical 6 over 2, and 1. Those are the rectangular coordinates. In the next example, we are given rectangular coordinates, and we would like to find the spherical coordinates for this point. So to help us with this, I think it is a little bit helpful to have a graph. So let's attempt to graph this. So when graphing, we have an x-coordinate of 0, so we are not going out at all on the x-axis. We have a y-coordinate of 2 radical 3, so we go a distance of 2 radical 3 on the y-axis. And then we're going to go down 2 units on the z-axis. And so 2 radical 3 is right about here. And 2 units on the z-axis, if I just continue this down just a little bit there, 2 units down on the z-axis is right about there. And so the coordinates of that point would be approximately right there. Okay, and if you want, you can draw that. All right, now what we know is that the angle theta is the angle from the positive x-axis over to this point. Well, since this point is directly below the y-axis, we know we're rotating through an angle of theta equals pi over 2. Also, in this right triangle right here, we know that this side is negative 2 and this side is 2 radical 3. This means that the angle right there is 30 degrees. And so the angle from the positive z-axis down to there is going to be 90 degrees plus 30 degrees, which is 120 degrees, which of course in radians is 2 pi over 3. And so that's phi. And then rho is just the distance from here to here. So you could use the Pythagorean theorem with these two sides to find out how long this is. Or if you know that in a 30, 60, 90 triangle, the hypotenuse is always twice as long as this short leg here, we know that rho is 4. So in spherical coordinates, one answer is this. Now I say one answer because remember angles can be coterminal, and so we can plug in different values for these angles and still get the same point here. So now let's talk about graphs in spherical coordinates. Certain graphs are very easy to describe using spherical coordinates. For example, the equation rho equals c is simply a sphere because theta can be any angle, phi can be any angle, and c just represents the distance from the center, from the origin out to a point. And so that is clearly a three-dimensional circle, which is a sphere. If I have theta equals some constant c, this is simply going to be a half plane at that value of theta. If I say phi equals c, phi, remember, is the angle from the positive z-axis down to where you're at there. And so since there's no restriction on theta, we know that we have to be angled this far away from the z-axis, but we can encompass any angle theta around it. So this is going to give us a half cone. And if theta is equal to some, if phi is equal to some constant c, where c is bigger than pi over 2 but less than pi, that's just going to be a half cone down below the xy plane. So there are certain types of graphs that are easy to describe using spherical coordinates. And it's really when we're dealing with these kinds of graphs and functions, that's when we want to use spherical coordinates. We don't have any reason to use spherical coordinates if the graphs do not lend themselves to be more convenient when using spherical coordinates. So now let's look at triple integrals in spherical coordinates. The thing to keep in mind here is that the region in our domain is some volume. And what we have to do is partition that volume into a bunch of smaller volumes. When working in spherical coordinates, that partition is going to resemble a block that sort of looks like this. So it's not a perfectly square block, but we can approximate the volume of this block by simply multiplying the length here times the width here times the height here. And so since this measure right here is rho, the distance from here to here is simply the change in rho, or d rho. This distance right here can be found by using arc length, and we know that this angle down here is equal to delta theta. And so all we're doing to approximate this length is taking the angle multiplied by the length from here to here. And that is rho times the sine of phi. And then over here, we can approximate this by simply taking rho and multiplying it by d phi. Okay, so d phi is the angle here, and rho is the distance, and we know that to get an arc length, we simply take, basically it's the radius multiplied by the angle there. So the volume of this box, this chunk here, is going to be the product of rho sine of phi delta theta, rho d phi, and also d rho. And when you put all those together, you get rho squared sine of phi times d rho d theta d phi, and that is what you see here. So the dz dy dx gets replaced with this, and then of course x, y, and z simply get replaced with what they are equal to in polar coordinates. Okay, now this is when your region E is a spherical wedge. So rho is between two values A and B, theta is between two values alpha and beta, and phi is between two values C and D. Let's do an example. So here we want to evaluate the triple integral of the function e to the power x squared plus y squared plus z squared to the power 3 halves dv, where B, the domain, is the unit ball. So let's remember that the unit ball is basically just a sphere of radius 1 unit. So it looks something like this. And we know that this can be described by the equation rho equals 1. And if we're looking at all of the points inside of this ball, then we would say rho is between 1 and 0. Now, to get the spherical ball, theta needs to go from 0 to 2 pi. And phi needs to rotate from the positive z-axis. Phi needs to rotate from 0 all the way down to pi. So this is going to be our spherical wedge. These are the limits of our spherical wedge. Now all we have to do is plug it into the formula. So let's recall that rho squared is equal to x squared plus y squared plus z squared. So in the function here, I'm going to replace x squared plus y squared plus z squared with rho squared. And then that's raised to the 3/2 power, and then we have e to that. So that's just going to be e to the rho cubed. So we're going to have the triple integral. We have e to the rho cubed. And then don't forget the rest of the formula. So in addition to that, we need to have rho squared sine of phi, and then d rho, d theta, d phi. So let's go ahead and put that in. We have rho squared sine of phi, d rho, d theta, d phi. And then we're going to integrate with respect to rho first, and rho goes between 0 and 1. And then theta is next, and theta goes between 0 and 2 pi. And finally, phi goes between 0 and pi. And now we just need to integrate like usual. So integrating with respect to rho first, sine of phi is a constant. Let's just go ahead and take a look at the integral of e to the rho cubed times rho squared d rho. I'm going to let u be equal to rho cubed. du will be 3 rho squared d rho. And so this becomes 1/3 integral of e to the u du, which is 1/3 e to the rho cubed. Okay, so that is the antiderivative of this part. Then, of course, we have to evaluate that from 0 to 1, and don't forget to have your constant sine of phi there. So this part of the integral right here, this part right here, is going to end up being 1/3 e to the rho cubed sine of phi evaluated from 0 to 1. When we plug in 1 for rho, we get 1/3 e sine of phi, minus, when you plug in 0 for rho, e to the 0 is 1, so we just get 1/3 sine of phi. Getting a little crowded over here. Let me take this out. Okay. And now that is what we're going to integrate next. And so this integral becomes the integral from 0 to pi, integral from 0 to 2 pi. And then right here, if we want to, we can factor out the sine of phi. So we're going to have 1/3 e minus 1/3 times the sine of phi, and then d theta d phi. Now this can actually be factored completely out because it's just a constant. So if you want, you can actually pull that out to the beginning, and you can take the 1/3 out, and then you'll have e minus 1. I do think it's worth it to do this because it just makes everything a little bit cleaner on the inside. Oops, this is d phi. There we go. All right, now performing the integration. Next integration, we're going to integrate with respect to theta. This is a constant, so the integral of sine of phi is simply theta times the sine of phi. So let's focus on this integration next. That's going to be theta sine of phi, where theta goes from 0 to 2 pi. So that is 2 pi sine of phi minus 0 times sine of phi, which is just 2 pi times the sine of phi. So this becomes 1/3, the 2 pi I can pull out. E minus 1 is already pulled out, and now I have the integral from 0 to pi of just sine of phi, d phi. And this last part here, integral of sine is just negative cosine. And we go from 0 to pi. It's going to be negative cosine of pi plus cosine of 0, which is negative 1 plus 1, which equals 2. And so we're going to multiply all of this by 2. So our final answer, we have 1/3 times 2 pi times e minus 1 times 2. And this is 4 pi over 3 times e minus 1. And for our second example of integration using spherical coordinates, and this will be our final example for the section, we would like to use spherical coordinates to find the volume of the solid that lies above the cone, z equals square root of x squared plus y squared, which is this cone right here, but below the sphere, x squared plus y squared plus z squared is equal to z. Now, this equation right here, this is nothing more than a sphere whose center is at 0, 0, 1/2, and whose radius is also 1/2. Now, to see that, you could complete the square here. So you could rewrite this equation like this. And then you can complete the square by taking half of this number there and squaring it, and then adding that number to both sides. And then you can factor this now. This becomes z minus 1/2 quantity squared is equal to 1/4, which is 1/2 quantity squared. And this is a sphere whose center is 0, 0, 1/2, and whose radius is also 1/2. And that is the sphere that you see here. Okay, so when you want to find a volume of your domain, all you have to do is integrate with respect to v the region, okay? The region that I will call D here. Now, the tricky thing here is that describing this domain in rectangular coordinates would be very complicated. So what we're going to do is use spherical coordinates instead. So what we need to do is describe this domain. So let's first recognize that theta is going to have to rotate between 0 and 2 pi to capture this whole domain. So we know that theta needs to be between 0 and 2 pi. Now, phi is the angle from the positive z-axis, which is considered to be phi equals 0, and we have to rotate down to this mark here. Well, that angle is pi over 4, okay? So phi has to go between 0 and pi over 4. And then what is rho? Well, let's think about it this way. Rho is the distance from here to any point on this sphere or within this sphere. So clearly the minimum length of rho is going to be 0. So we know that rho is going to be between 0 and something. But what is the biggest that rho can be for a particular angle phi? Okay, so all you have to do here is use some trigonometry to figure out what rho has to be. So here's rho right there. Okay, now so to capture this value of rho, we're actually going to draw a segment from here to here. And I'm going to make the case that this is a 90-degree angle. In geometry, we learn that if we have a point on a circle and it intersects the circle here and here, thus making an angle, this angle measure is always half the angle measure of the arc here. But this is a 180-degree arc because it is literally half of this circle or half of this sphere. Therefore, this angle is always going to be 90 degrees. Now, as soon as we know that, we can express the length of this side by using this right triangle to do that. Now, keep in mind, we know that the distance from here to here is 1 unit because that is the diameter of the sphere. And so we can see that rho is going to equal 1 times the cosine of phi, just using right triangle trigonometry. And so the maximum value of rho is going to be cosine of phi. Okay, so now we're ready to set this up. Okay, so now this triple integral becomes the integral from 0 to 2 pi, the integral from 0 to pi over 4, integral from 0 to cosine of phi of dv, which is rho squared sine of phi d rho d phi d theta. So our function here is just the function 1, and so that doesn't change in here. All right, so now let's go ahead and integrate this with respect to rho. So I'm just looking at this part of the integral. Let's do the math there. The integral of rho squared is 1/3 rho cubed. Sine of phi is a constant, and we go from 0 to cosine of phi. When you plug in 0, you get 0. So we just need to plug in cosine of phi. So this becomes 1/3 cosine cubed of phi sine of phi. All right, on to the next step. So now the integral we have is the integral from 0 to 2 pi, the integral from 0 to pi over 4, and then we've got 1/3 cosine cubed of phi sine of phi d phi d theta. And again, now I'm just focusing on this integral. And so that one can use a u substitution. So let's just pull that integral out real quick here. Remind ourselves how to do trig integrals. And this goes from 0 to pi over 4. So we have u equals cosine of phi. du is going to be negative sine of phi d phi. And this integral becomes negative 1/3 integral of u cubed du. This is a cube here. There we go. And when you do the integration, you will get negative 1/12 u to the 4th, which becomes negative 1/12 cosine to the 4th of phi. And then now we're going to evaluate that from 0 to pi over 4. And I'm not changing my limits. You certainly could change your limits, but when you plug in phi equals pi over 4, you get u equals radical 2 over 2, and I would just prefer to just use my old limits. So this becomes negative 1/12 cosine of pi over 4 to the 4th power minus cosine of 0 to the 4th power. Now that is negative 1/12 radical 2 over 2 to the 4th minus 1 to the 4th. Now, radical 2 over 2 to the 4th power is going to be 4 over 16, which is 1/4. So in here we have 1/4 minus 1, which is 3/4 negative. So what we've got there is negative 1/12 times negative 3/4. And if you simplify that, you get 1/16. So now our final integral, if we come back here, is going to be the integral from 0 to 2 pi of that result, which is 1/16 with respect to theta. And this, of course, is 1/16 theta from 0 to 2 pi. And when you plug in 2 pi, you get 2 pi over 16, which simplifies to pi over 8. So it's a whole lot of details, but to be totally honest with everybody, the challenge isn't really the integration. The challenge, in my opinion, is describing this region using your spherical coordinates and determining the bounds on each of those variables. So I feel like this is the most challenging part of the problem. The rest is just semantics, going through and doing the integration. So what this really takes, of course, is a lot of practice. And that concludes this video lesson.